Today we're going to get the theoretical framework to learn about Gaussian quadrature, which just let me tell you is just a magnificent way of calculating integrals. We're going to have to lay down a theoretical basis for it, and we're going to start out defining an inner product. We're going to have w of x be a function that's positive on the closed interval from a to b, and given functions f and g defined on the interval from a to b, we're going to say the inner product of f with g is the integral from a to b of f times g times w dx. Okay. So given this definition, I mean, what's happening here? You're putting in functions and it's going to spit out a number for you. It's easy to go through the definition and check that the inner product of f with g is equal to the inner product of g with f, that the inner product of a real number f with a real number a times f plus a real number b times g is equal to ab times the inner product of ag, that f inner product of f plus h is f inner product f inner product g plus f inner product h, that the inner product of f plus h with g is the inner product of f with g plus the inner product of h with g, and finally the inner product of f times h with g is the inner product of f with h times g. So otherwise we can make the h hop the comma here. Now this is all done in analogy to the inner product of vectors, or the dot product of vectors. We're going to say that f is orthogonal to g if f inner product g is equal to 0. And again, if the value, that's exactly saying the value of this integral is equal to 0. Okay? So what we're going to be thinking about is approximating this integral f of x times g as the integral from a to b f of g is approximately equal to the sum of I equals 0 to n of ai times f of xi, where my ai will be the integral from a to b of li xi wi. Li of x times wi. So presumably, this Li times x wi is something that's easier to integrate by itself than this is. Okay. Now, suppose that we have an approximation 1 with the coefficients as in 2, chosen where my knots x0 through xn are the roots of a roots of q, okay, a polynomial q. And suppose that q is orthogonal to f for every polynomial of degree n. Then the approximation formula given in 1 will be exact for all of those polynomials of degree 2n plus 1. So this is saying for a nicely chosen polynomial which is orthogonal to all of this, if we know its roots, okay, then even though it's orthogonal to only polynomials of degree n, the integration is going to be exact for polynomials 2n plus 1. So we get twice and then one more. So this is good, okay, provided you can find your polynomial q. And so let's prove it. This is something that we can actually prove nicely. Suppose that f is one of these polynomials of degree 2n plus 1 or less. Okay. So then we can divide f by q. Okay. And we'll get the degree of p is going to be the original degree of f minus the degree of q, which will be 2n plus 1 minus n plus 1, and so that will equal n. Okay, and why is q degree n plus 1? Well, because it has n plus 1 roots. Okay, and then this polynomial r is going to be of degree less than n. This is, you know, the division algorithm for polynomials. Okay, now let's think about it. The inner product of f with 1 is the inner product of q times p plus r plus 1. We use the properties of the inner product to break this sum down. And so, see, this inner product is chosen, right? We put the 1 with the inner product, say this is just the integral of f times w, okay? And so we do this, and by since this polynomial p is of degree n, okay, this is orthogonal to it, okay, and so that goes to 0, and so we're only left with this integral with r1, which we can approximate exactly using the method because it's of degree less than n, okay. So therefore, now look, what we have here is if I evaluate my f at xi, that's the same as evaluating this qpr plus r at xi. Well, it's the xi is the root of this q, so this term falls out. We're left with the ri. So my r evaluated at xi is equal to my f evaluated at xi. And so I get this formula dead on accurate right there. This is it's amazing. We'll take a look and see how this looks in application. So I have here my Jupyter spreadsheet set up. I'm going to import some functions from NumPy. I'm going to import square root, import sine, and import pi. I'm going to say alpha is equal to 1 over the square root of 3 because it's the root of one of my, it's the root of my polynomial, one of the roots of my of a quadratic polynomial that is like q, okay? All right, so I shift and enter. Now I define my quadratic polynomial here, my Gaussian quadrature formula. F is the function I'm going to integrate, and a, b is the interval I'm going to integrate it on. I put this in as a function as a change of variables, okay? And then I return the answer. I'm I'm doing just evaluation on these polynomials as one does in Gaussian quadrature. So I start off with my test case, integrating a cubic. And so shift, enter, and it gives me 0.25, which is exactly what I should get here. Okay. On this one, I'll do, this is a function I don't know, I don't know exactly, but just to show that, I'm integrating it, it's a sine of t over t, okay, and I get 0.946. Is that right? I don't know, but okay, let's integrate for sine. The integral of sine over the interval from 0 to 2 pi. All right, that should give me 0, shouldn't it? Because anytime you integrate a sine or a cosine over its full period, that gives you 0. Well, we go shift and enter. Hey, and it's negative 6.9 times 10 to the negative 16th, which, it's not 0, but it's close enough for jazz. Okay.